Python. Now, before we start Python, let me show you one thing. As I said, the weights and nodes are available on the net, and what I've done is I've simply looked up such a page on the internet by googling it, and from that page I've just copied out the 32-point Gauss quadrature weights. That particular page had many other Gauss weights and nodes for other values of n. I've just copied down Gauss 32. Oops, there is no, the file name is wrong. It's not Gauss32.txt. I had Gauss32.dat. So as you can see, this actually comes in 3 columns, and obviously the first column here is just the serial number. The second column has only positive numbers, and each is of the order of 1 by 10 or smaller. After all, there are 32 of them and they have to add up to 1. These are the weights. These weights, if you look carefully, you will find that each successive weight is actually equal. So these two are equal. So are weights number 3 and 4, weights number 5 and 6, and so on. And if you look at the node values which are listed in the third column, you will find node values for these same weights are really negatives of each other. So this is a symmetric property of the Legendre, which follows from the symmetry of the Legendre polynomials. The nodes occur in positive and negative pairs. So if you are ever confused which column is a node, which one column is a weight, the one with negative numbers are nodes, and the other column, the column with only positive numbers, is the one with the weights. Here the 0th column, remember counting starts at 0, is just a bunch of serial numbers. The 1th column and the 2th column are the weights and the nodes respectively. So let's just remember that 3 columns, serial number, weight, node. Now let's start Python and import numpy as np. Okay. And now that I've imported numpy as np, what I will do is I will try to integrate a function. Let's say I'm using lambda to define the function. So x maps to, let's say, x to the power 100. So since we are doing 32-point Gauss quadrature up to 63 degree polynomials, the result should be exact. For x to 100, the result is not going to be exact, but let's see how good the result is going to be. Of course, the answer, we are going to do basic Gauss quadrature first, which means integral from -1 to +1. The correct answer is 2 by 101. So we expect to get pretty close to that by using 32-point Gauss quadrature. So this is the function set up for us. What we need are the weights and the nodes. As we have seen, these weights and nodes are in a file which is called Gauss32.dat. So what we do is we use the numpy function load text, and load text takes, at the very minimum, it takes one argument, which is the name of the file that we are trying to load. So in this case, Gauss32.dat. Of course, the name is a string. It has to go within quotes. Now, if I use this, what numpy will do, or what the load text function will do, is that it is going to import the entire contents of the Gauss32.dat file and load this into an array. There are other arguments that we can add to the load text. For example, it has a skip rows argument, which tells you that you can skip that many rows at the beginning. It has a max rows argument which tells you how many rows to take. By default, it simply is take all the rows. It also has a useCalls argument which tells you which columns of the file to pick up. But right now what we are going to do is we are just going to load the whole thing. And just take a look at the shape here. The shape is 32, 3. Of course, it's a two-dimensional array of which along the 0 axis you have 32 entries which we interpret as 32 rows. Along the 1 axis, which is the axis along which different columns are, you have 3 entries. And what we need to do is now separate them up into weights and nodes. So we need an array of the weights and weights alone, and we need to slice it out of the array V. Now this is where the tricks that we learned about slicing comes in. Notice that here you have 2 indices because this is a two-dimensional array, and what we need to do is to tell Python how much of each axis do you want in a slice. So for the 0 axis, which is the first axis, 0th axis, we need all the 32 entries. So we need all the 32 weights, which is why the slice does not specify a beginning or an ending. It's just a colon without anything in front and back. That simply means take everything. So that's for the 0th axis. For the 1th axis, for the weights, we need to take only column number 1. Remember, column number 0 was the serial numbers, column number 1 was the weights. So I just write W's equals V square bracket colon comma 1. The square bracket colon means take every value of every one of the 0 to 31 values which are there along the 0 axis, and the one here says take only the index 1 along the axis number 1, which means only the second column. Well, these are the W's. What are the X's? Very similarly, it's going to be all the rows and only column number 2, the third column. So we have got our W's and X's. So now that we have our W's and X's, calculating the Gauss quadrature formula is trivial. All you need to do is this. We calculate f of x's gives an array of the function values at the nodes. That's it. And what you can do is simply multiply this by the array w, so each of the function value will get multiplied by the corresponding weight, and then we could use np.sum. Or, as you may remember from what we had done before, just use this is just like the dot product, and this is straightforward. It works out fine, and you end up with this value. Just to check whether this is any good, let's multiply this by 101. I get 1.9999, quite a lot of 1.9s. In fact, this is 1, 2, 3, 4, 5, 6, 7, 8, 9. The difference is in the 10th decimal place. So our result is correct to a pretty high degree of accuracy. So this was for x 100. Let's try x 1000. If you remember the lecture on Simpson's one-third rule, with x 1000 you needed pretty high number of points in order to get pretty good accuracy. Let's try to do this for Gauss quadrature, 32-point Gauss quadrature. The weights and nodes are already there. All we need to do is calculate the value of the function, this new function x 1000, at every point on the axis just by applying f on x's, and take the dot product of that with w's. And let's see whether this is really any good. We need to multiply this by 1001 the exact result is of course 2 by 1001. This is coming out to be pretty bad now. So with 32 points, you are not going to get a very accurate result for a polynomial which is not, or for any function which is not well approximated by small order polynomials. It's 100, you got a reasonably good result. It's 1000, not so much. Which is why you need to have error estimates. Here the error estimate of course was easy, we knew the exact result. But because in general we will not be in a position to know the exact result, we need to calculate the Gauss quadrature values. Then we need to calculate the Gauss-Kronrod, the Kronrod estimate, and then get an estimate of the error from there, and then decide whether we want to divide up the interval into smaller pieces and go ahead. And just to sort of round off this Gauss estimate thing, let me just briefly point out what happens for a general interval. So let's say we want to integrate the function sine square x from 0 to pi. Okay, so let's define the function again. I'm being lazy and keeping on calling all functions f, and I'm using lambda for all of them. So this is np dot sine x whole square. The exact result for this of course is pi by 2 if you want to integrate this from 0 to pi. So a is 0, b is np dot pi, and we want to evaluate this using 32 point Gauss quadrature. So what we need to do is firstly multiply the result by b minus a by 2. Let me just remind you of where this came from. Yeah, this is b minus a by 2 times the weighted sum of f at these points. So this formula will be peeking out from under the terminal, so you can see whether I'm doing it right, of the w's. Remember the dot product, at least for same size arrays, is commutative. You can do it, write it in any order you want. And f of, well, f not of the excess but of this. So I'm just taking this formula. Remember, this multiplication of an array by a scalar, just a number, is element by element multiplication. This gets added to every element as you have in the formula here. The function gets evaluated for every one of these shifted excess values, and then is dotted with the w's. And this is the result. And just to check whether this is really close, let's divide pi by the answer and see whether I get 2. Well, I get almost exactly 2. Let me just see np dot pi by 2, how much is that? To within machine accuracy, this is exactly the result we have. So 32 point Gauss quadrature works rather well here. After all, the sine square function is estimated rather well by low order polynomials. So a pretty good match here. Now, can we do Gauss-Kronrod using similar procedure? Of course we can. For that we will need a file which tabulates for us the Gauss nodes and weights and the Kronrod nodes and weights. I actually have such a file. So let me just switch to a new tab so that I can show you that. So there's a 715 Gauss-Kronrod. So 7 point Gauss, 15 point Kronrod, 8 extra points. This is actually quite common. This file we have only two columns. The 0th column has the nodes for 7-point Gauss. Notice again that the nodes appeared in positive negative pairs except for 0, of course. There is an odd order Gauss quadrature, which means you are using P7 here, so 0 is a node. For even order, 0 is not a node. So the other nodes are at symmetric positions on both sides of 0, with weights being symmetric and so on. So these 7 points, the first 7 rows contain the 7 points there. Then you have 15, a blank line, then you have 15 rows which have the Kronrod nodes and weights. Just let me point out one thing, that this point, for example, this point here, 0.9491079, etc., is used in Kronrod. This actually is also used in Gauss quadrature. So Kronrod quadrature and Gauss quadrature both uses these points. At least the 7 points which are used in Gauss quadrature are also used in Kronrod quadrature. The weights are very different. Of course, these 7 weights have to add up to 1. Here we have 15 weights which add up to 1. So the weights are very different, they are calculated differently, but we don't need to worry about that because that's available on the net readily in the form of tables. So the only tricky thing about carrying out Gauss-Kronrod 715 quadrature with data which is there in this file is to read the file properly. After all, the top 7 rows are the ones which we are going to use for Gauss. The last 15 are what we are going to use for Kronrod, and which means 8 rows from the top has to be left out. As I said, load text actually has all these options, and just so that you can figure it out yourself, let me show that if I try help np.load txt, we get a message which is sort of being difficult to read in my highly magnified font, but you can see it says load text, then file name, data type by default is float, lines with hashes are comments, so they will be ignored. So if the 8th blank line there had been just a hash, that would have been fine for us. And what is important for you is skip rows, which by default is 0, which shows the row counting starts at 0. So there you would have to count the number of rows starting from 0, the ones which you want to skip, to get the Kronrod weights. And you also have max underscore rows, which says how many rows to take, which by default is none, so goes all the way to the end. So you want to extract the Gauss nodes and weights, you need to use load text with the file name and then say max underscore rows equal to 7. For Kronrod, you have to say skip rows equal to 8. So the first 8 rows are skipped. Okay. This is an exercise I am going to leave for you. So I am going to provide both the Gauss nodes and weights, the file, and the Gauss-Kronrod nodes and weights, the file, in VLearn. You should be able to download them and use them to calculate integrals using both the Gauss procedure and the Gauss-Kronrod procedure. Okay. And in the next part of the lecture, we are going to talk about how to use the SciPy integrate module.